we're putting together to try to talk about the marsh and other aspects of conservation in Scarborough. And tonight's speaker is Pete Slovinsky. Sorry. Pete is a marine geologist. He works for the Maine Geological Survey and the Bureau of Resource Information and Land Use Planning. Is that still correct?
Brilliant, yes.
Brilliant? Okay. Pete's a resident of Scarborough. He has also been chair of the Conservation Commission in Scarborough. And he has asked that you kind of save your questions till the end, just to make
We'll
it
have
a
more
little
than
bit,
enough time.
flow more easily. So with that, I told you it would be a 2-minute introduction.
That's
It's all yours, Pete.
Yeah, so I'm gonna.
I'll get the
You
lights.
get the lights, okay. So I don't have a pointer, so you'll see me walking in front of the screen occasionally. So thanks for coming out tonight, and on the, I guess, oh, you are awesome. I can stay in the back of the room. Seriously, thank you for coming out tonight, everyone. This is a wonderful, I guess, end of summer night, I guess we could say. I think tomorrow the fall weather comes in. So I'm going to give just some information on some of the work that we've been doing at the Maine Geological Survey as it relates to sea level rise. I'm going to go talk a little bit about what we've been seeing in terms of current trends on sea level rise, what some of the potential future scenarios are. And then we're going to take a look at what might actually happen to the Scarborough Marsh in response to those scenarios. And what's interesting also is I'm going to bring in some infrastructure into this, because we can't think about the marsh and how it might move without thinking about how infrastructure may be in the way of the marsh moving, or what might also be happening to that infrastructure in response to sea level rise. So I'm going to be showing some stuff towards the end about impacts to roads and also to the Pan Am rail line, which might be kind of interesting. So if I can see my, all right, there we go. So when we think about sea level rise, we have to think about a global scale of things that are happening. And there are several very dominant processes that are driving the changes that we're seeing on a global scale. Okay? Some of them are impacting what's happening on a local scale. We'll talk about that in a little bit. But on a global scale, two dominant factors that are driving changes for global oceans are basically the melting of land-based ice sheets and glaciers. Most people think of Antarctica and Greenland. There are other land-based glaciers that are also influencing, but that accounts for about 50% of the change that we're seeing in modern-day sea levels. Okay? About 40% is attributed to the concept of thermal expansion. So basically the water column is heating up and it's expanding. Okay, that's about 40%. And 10% is due to a variety of different factors, including changes in how we manage our groundwater, terrestrial storage basically, isostatic adjustment of the land surface, is it rebounding in response to glaciers, is it still sinking, what is it doing in terms of relation to the groundwater or the hydrocarbons that we're withdrawing, changes in ocean circulation, and I'll get into that in a second. That can have a big impact on local sea level changes. And then gravitational changes, believe it or not. Actually, as Antarctica and Greenland become smaller and shed ice, their gravitational pull decreases. The sea level around it actually falls. But the sea level away from it actually rises. Okay? But those are small factors that account for about 10%. All right, so focusing on the dominant factor of volumetric increase, this is a plot of, and I'll show you a bunch of graphs because I'm a scientist. I'll throw all the boring graphs out at the front, and then we'll talk about the cool stuff later. This is basically, these are mass variations since 2002 of Antarctica and Greenland. It's clear what the overall trend is since 2002. Okay, we're seeing pretty systematic. There's some seasonal signals in here, but we're just seeing loss of mass, and we're seeing loss of the average thickness of most land-based glaciers. Okay, so that is contributing significantly, about 50%, to the sea level changes that we're seeing. The other factor that's important is thermal expansion. This is a little complex, but this basically is showing how much heat is trapped in the upper couple hundred meters of the world's oceans, compared with an average from 1955 to 2006. So anything that's blue is below that long-term average, and anything that's this yellow color is above. So right around 1990, we've been consistently above. So this is telling us that the oceans are heating up. Okay? And as you probably have read, The Gulf of Maine is heating up faster than a lot of the water bodies around the world. So as a result, you combine those two things, plus that little 10%, and sea levels on a global scale have been changing at about 1.8 millimeters per year. That doesn't sound like much. It's only about 7 inches per century, okay? So keep that number in mind, and let's take a look at some other things. So, over the last 20 years, sea level has actually accelerated. The change in rate of sea level rise has accelerated. And that's actually measured around the global oceans by satellites. Satellites are constantly going around the world, and there are satellites out there that can measure the surface of the ocean and how it changes. The surface of the ocean is not static. It's not the same all around the world. But this is an average and change in mean sea level that's showing over the last 23 years, the rate of sea level rise on a global scale is up to about 3.4 millimeters per year. So it's almost a doubling. Remember, 1.8 for over the last 100 years, 3.4 over the last 25. Now, I always like to take things from a global scale and bring them down to what's happening near us. And this is a similar chart. This is a graph from annual sea levels from Portland, so just up the coast, from 1912 all the way through 2016. And you can see a lot of variability in here, but the overall trend is this linear trend right here. And it's at 1.9 millimeters per year over a century scale, basically. So it's right in that 7 inches per century mark. What's interesting, if you look at the last 24 years, and I'm certainly not saying that we should cherry pick data and look just at where these trends occur, but if, this is what's happening on a global scale. The last 24 years, 3.4 millimeters per year. Over the last 24 years, roughly, we're at 3.1, roughly, millimeters per year, plus or minus 1 millimeter, because of all this variability here. So we've also seen a little uptick. Now, this was 2010, and you've seen it's fallen since 2010, but this 2016 number is still much higher than the overall long-term average, which is this number here. Okay? 0 basically is the long-term average from 1912 to 2016. But what's interesting is that sea level can change abruptly. So this 2010 outlier, we're calling it, is a result of several things, and we'll talk about that in a second. But most people think about the sea level change as something that's just happening a millimeter at a time, per decade, very, very, very slowly, something that happens over somebody's lifetime. This happened in basically a year. What caused it? So, sea level can change abruptly, and what caused the deviation that we saw in 2010? Sea levels were on average about 5 inches higher than normal for almost the whole year of 2010 and a good portion of the end of the year in 2009. To put that into context, there's only a 1 foot difference, or 12-inch difference, between our 10-year storm event. So that's an event. The Patriots Day storm is a 10-year storm event. Has a 10% chance of occurring in any given year. And what's called our 1% or 100-year storm event, that has a 1% chance of occurring in any given year. There's only a 1 foot difference between those two things. So if you have sea levels that are running 5 to 6 inches higher, you can have significant impacts. So that's exactly what happened. So the two dominant things that cause that: the Gulf Stream basically pulls warm water out of this gyre and pulls it northwards up towards the Arctic. Okay? It sinks over a long period of time and then slowly returns, but that's not key here. What's key is when the Gulf Stream slows down, which is what it did in 2010, it's a very fast-moving hot water body of water, and you can literally track that it's moving faster and the temperatures are much higher. When it slows down, this is the Sea of Sargasso, it's called. The sea level in this area is actually propped up by this gyre, or this subtropical recirculation of the Gulf Stream. And when the Gulf Stream slows down, water can slosh against the east coast of the United States. That's exactly what happened. That was one of the factors. This slowed down, so water sloshed against the coast. The other thing that happened is something called the North Atlantic Oscillation was in a very negative phase. We don't need to get into all the mumbo-jumbo for that. It's basically how pressure systems set up over the Azores and Greenland. And when they set up in a certain way, in a negative phase, there's low pressure out here, very low pressure sitting off the east coast. What does a low pressure do? Pushes wind onshore. So we had very light but persistent onshore winds which pushed water against the coastline. Okay? So water's stacking up against the coastline. Add on top of that, in a negative phase, the jet stream dips all the way down to Florida. If you remember, 2010 was a snowy, cold year. We had a lot of nor'easters and it was cold. And this jet stream dip is a perfect track for winter storms to go right up our coastline, and zip up our coastline. You combine all those things together, and in 2010 we had 5 of the highest monthly sea levels over the last 100 years occurred in 2010. As a result, this is Higgins Beach. This is a 3,000-year-old marsh surface, which I talked to folks that have been there for 55 years, and they said they've never seen this. So there's usually about 3-4 feet of sand on top of this. And it was eroded out because of that higher sea level and all those winter storms. Okay. So I'm just putting this into context of additional information. It's not related to the marsh, but the sea level is what's driving some of the changes we see at the marsh. All right, this is, I promise, this is our last graph. Where might things go in the future? This is a tough question to answer, but the scientists, much smarter than me, are working on this. And some of the best scientists that NOAA can pull together, they write a technical report each year that that comes out before the National Climate Assessment does. Okay? This report was published in January of 2017. And what it's doing is it's taking the tide gauge data we have, the satellite data we have, and then it's plugging all of the forcings that occur with different models of global warming, basically, and saying how much sea level might potentially come out of that. Okay? This lowest scenario, 1 foot, is basically what happened over the last 100 years is exactly what's going to happen over the next 100 years. Almost everyone that I know, and myself included, discounts this completely. We're setting a new norm. What happened over the last 100 years is not going to happen over the next 100 years. We've already put more heat into the oceans than ever before, so they're going to respond. So this is nothing to even consider. 1.6 feet, roughly 2 feet, is something to consider. This number came out from only taking into account thermal expansion. Okay, when that number came out. The scientists couldn't qualify enough of the input from Antarctica and Greenland, so they said, you know what, this is the IPCC. That's where this number comes from. They basically said, we're not going to include it. 1.6 feet. When you start including Antarctica and Greenland, again, 50% roughly, you're in this 3 to 6 foot range roughly. Okay? And then they threw this other number out here, which is 8.2 feet. That's considered the, quote, extreme scenario. It has less than 1% chance of occurring, according to these scientists. But they put it in here because the science behind how fast Antarctica and Greenland are melting isn't 100% there yet. We're learning something new every day. Okay? So they put this extreme scenario in here. There's talk about 20 feet and all that. I don't think anybody in the right mind says we're going to see 20 feet by the year 2100. Okay? Beyond that, possibly. So anyway, the range we like to look at when we think of these things is somewhere from the 1 to 6 foot range. Using the 1 foot range is, I like to use it as a scenario for something that might be around in about 2050 based on the current melting rates. So, thinking about all that, how do we actually simulate what might happen to Scarborough Marsh? Well, we use data called LIDAR, Light Detection and Ranging it stands for. So basically an airplane flies over the ground and shoots lasers at the surface of the earth. The lasers are traveling at a known speed, they bounce off trees, they bounce off the marsh, they don't penetrate the water, so on water it doesn't work. You have to use a different colored laser for that. And it bounces back to the plane. The plane knows how fast it's traveling and how high it is, and we know how fast the laser can move. So with that, you can create what's called a digital elevation model. Now this model includes trees and houses. We run that through different algorithms that filter that out, and you end up with what's called a bare earth model. It's very cool technology. This is a bare earth model for Scarborough. This is the Scarborough Marsh area right here. This is Pine Point, Browns Neck, Scarborough Beach, Higgins Beach. Okay? And I'm pointing at an arrow right here because the first thing I did when we got this data is I said, I don't believe it. I want to make sure it's accurate. So, in nice weather, my intern and I went out and we walked the entire big section of Scarborough Marsh, and we put GPS points. This GPS that we're carrying here, it uses satellites and a little base station and all that, but it's accurate to about the size of a quarter, horizontally and vertically. The one that you have on your phone is accurate to about from the ceiling to the floor, vertically, and probably about from this portion of the room to the middle of the room, horizontally. Okay, so it's very, very accurate. So we take elevations on the marsh and we compare with the LiDAR to see if it's accurate. And sure enough, you don't need to pay attention to these numbers, but I've sampled 3,500 points in 22 different municipalities around the state. We found that basically it's accurate to about 6 inches, which is right where we want it to be. Okay? So the LiDAR represents the surface of the Earth, including the marsh surface, very, very well. Okay, so what does that actually mean? What do we then do with it? So there's a definition out there for a coastal wetland that is in Maine's municipal shoreline zone that relates to the highest tide level for each year, basically what's called the highest annual tide, or HAT. So that corresponds with the upper boundary of a regulatory coastal wetland. It just so happens that it coincides with approximately the boundary of the vegetation we see in a coastal wetland. There are other tidal elevations out there that are very important. The coastal wetland basically extends, you go out and look at the marsh, it extends from roughly highest annual tide down to what's called mean tide level, which is the average height of the ocean surface, okay, above mean high and mean low tide. Mean high water is the average daily high water mark. When you walk out onto the marsh and look out there, you see some distinct different vegetative species. Some species like to grow closer to the mean tide level. That's usually the low marsh area, that tall cord grass grows out there. Meanwhile, other areas only like to get wet on the higher tides, or maybe only the highest of tides, and that's from roughly mean high water to highest annual tide. That's your high marsh, okay? But the overall marsh extends from mean tide level to highest annual tide. So this is just a color-coded infrared image showing, this is Ferry Beach right here. This is the backside of Pine Point. Jones Creek is right here. This goes up to the Railroad Bridge, and then Eastern Trail is up here. Showing uplands in dark red. You can see these gray areas. This is the high marsh, pretty much. And these fringing red areas in here are areas of low marsh, okay? So what we did is we worked with our Maine Natural Areas Program's colleagues, and they went out using an aerial imagery like this. They mapped the extent of coastal wetlands. We said, okay, that's great. Let's compare our LiDAR-derived coastal wetland to that. So my derived coastal wetland is this light green line. So it does a very good job of representing existing conditions on the coastal wetland. Okay? We kind of knew it would based on that LiDAR data, but this just shows us that we can use this data to do simulations. So what we did is we broke the low marsh to mean tide level to mean high water, and high marsh from mean high water to highest annual tide. And then these are numbers that you would see in a tide table. So, you look at mean high water, 9 feet is existing. You add a foot, that's 10.1 feet, 11 feet, 12 feet in these sea level rise scenarios. So we added these sea level rise scenarios to mean tide, mean high, and highest annual tide, and then broke the marsh up into its different components. So very quickly, I need to just go through some quick assumptions. We're using LiDAR data. It was flown in 2010. A lot happens in 7 years, potentially. The marsh doesn't change that much, but there are probably sections that have changed. So again, we're using a snapshot of topography that could have changed a little bit. We're using these tidal elevations. Remember, mean tide level, mean high water, and highest annual tide as proxies for the marsh. It's not going to be the exact boundaries of the marsh, but it's going to be pretty darn close. Okay? We also don't take into account where there are tidal restrictions when we're doing this kind of modeling. Okay, this modeling is called bathtub modeling. It's basically taking the water and moving it up. We're taking the marsh surface and moving it up in response to sea level rise. We're not taking into account sedimentation that could be occurring, and we're not taking into account erosion that could be occurring. So basically, all that said, what you're going to see is for general planning purposes only. All right, so let's take a look at what some of the stuff we see. All right, then you all know that area. So here's our marsh. This is the existing Scarborough marsh system. I'm not going up all the way into all the tributaries, just cutting it off where we have the majority of our dominant coastal wetland species. Here's the Spurwink River marsh system. And low marsh is the dark green. It's a little hard to see here, but it's all in this areas in here. And the light green is the high marsh. About 75% roughly of the existing Scarborough marsh system is high marsh. Same thing with Spurwink. 25% is low marsh. Okay, that's under existing scenarios. So what I'm going to do is I'm going to run through an iteration of images that show you what might happen to the Scarborough Marsh area with 1, 2, 3, and 6 feet of sea level rise. So just keep your eyes straight on these colors, and we'll go through them again so you can catch them all. All right, this is existing conditions. There's 1 foot. Okay, what do we notice from here to here? All right, we're seeing a little bit of growth in some areas of the high marsh into undeveloped uplands. But more importantly, we're seeing a significant change from a dominant high marsh to a dominant low marsh. Okay? One of the reasons that we're seeing this is, number one, there isn't now much topographic distance between the low marsh and the high marsh. So it can move a lot easier. There's a huge area of existing high marsh, so the low marsh can move into it very easily. The high marsh, however, is right now pinched against relatively steep sloped uplands in most areas, except for a few, including this area here, which we'll look at, and adjacent to existing development, whether it's roads or homes, okay? So it doesn't have a lot of room to move. So we'll go back one, and we'll start going through the 1, 2, 3, 4, 5, and 6. 2 feet, 3 feet, and 6 feet. Okay, and 6 feet. What's really interesting here is, there's a big difference between 3 and 6, but all this area that was marsh is going to convert probably to either open water or mud flats, all right? Because it's just going to be below mean tide level at that point. Where we have existing high marsh will mostly be low marsh, and where we had high marsh, or where we have developed and undeveloped uplands, that's where the marsh is going to try to move, okay? So let's take a closer look in this area here, because this is one of the largest swaths of undeveloped lands that sits adjacent to the existing marsh. All right, state and town-owned lands. So the town does own a big swath right in here, and it's surrounded by state-owned land here and state-owned land. This is Hampton Circle, I think it's called, right here. So this is the existing marsh again, green, dark green, low marsh, high marsh. So let's take a look at the changes in here. The reason I'm showing this is because this is, again, a great example of, this is kind of like a little bit of uplands, some freshwater wetlands and all that. These are the areas where our marsh can actually move into. So there's 1 foot, 2 feet, 3 feet, and 6 feet. So again, you see the difference between the greens, but also pay attention to what's happening out here, where the existing low marsh is. It's starting to turn into open water. Okay? So, I'm not going to go through all these numbers, but the key here is that there's a lot of room to expand with 1 foot, and that room to expand actually goes down a little bit. The overall coastal wetland in a 6-foot scenario is going to drop by 45% roughly, or 30% from the existing. And there is some room to expand, okay? That's one of the key things. There is room to expand, but if we have a large amount of sea level rise, we could see a lot of conversion to open water. Remember, I'm not taking into account sedimentation. So as water is moving up against the banks, you could have potentially more erosion, which could be feeding the marsh. Okay? Our marshes are keeping up with sea level rise right now. And most of the studies I've seen say from up to about 3 to 5 millimeters per year, we should be okay. Above that, don't know. All right. So summing this up, the existing conditions. This is the low marsh. This is the high marsh. 1 foot, there's a switch. 2 feet, there's dramatic loss of your existing high marsh, huge growth of the low marsh. Again, same thing with 3 feet. And with 6 feet, you have loss of both marsh systems. Okay, you're losing here a huge amount of open water. All right. So what might actually be impacted in terms of land types? What kind of land types do we have in this area? So what we did is we went and we took a whole bunch of different land types and grouped them into 3 things: natural, developed, and agricultural. Developed is like lawns, driveways, roads, houses. Agriculture is fallow fields, things that were farmed. And natural is forests, wetlands, things like that. Okay. So this is really busy, so I'm going to just skip through this. But this is the breakdown of developed versus natural and agricultural lands for the Scarborough area. Focus in on this area. This is the existing conditions. What we're going to do is we're going to just clip out the areas
are going to be impacted by sea level rise. So again, this is that area we showed before off Hampton Circle. You can see we're impacting mostly natural lands, not really developed lands at all. Mostly natural again. But this is a field in here that's going to be developed, unfortunately. And then 3 feet, and then 6 feet. Okay? That's where we're going to see some impacts to developed lands, potentially. So, but the take-home point here is that if you look at natural and agricultural lands, even under our highest scenarios, and our totals under these different scenarios, we're looking at approximately about 1,900 acres that the marsh can move into of land, with 1,600 of that being either natural or agricultural. Okay, so that's key. We have a lot of good land around the marsh for it to move. It's going to move. All right, now let's start looking at some other cool stuff. This I took during the high tide back, I think, in 2011. And this is just, it creeped up just a little bit more, but not too much. This image came out better. So this is Route 1, going through the marsh. Okay. Because again, we think about this is a perfect image in my mind because this marsh, you know, is connected to another marsh here. But for this to move through here, the water is going to be going over the road pretty soon. I mean, this is the high tide. So what we did is we looked all through Scarborough, and I was hoping these colors came out, and they did. We looked at all the major road systems. In fact, all the roads. So all the roads are in green. Roads that are impacted under highest annual tide. A little section of Pine Point Road right here that gets a little bit wet. Highest annual tide plus 1, 2, 3, and 6 feet are these different color-coded things. So the key here is, what do you see? With 1 foot, Route 1, boom. Pine Point Road, boom. Pine Point Road, boom. Black Point Road, boom. Sawyer Street, boom. The only way to get out of any of this whole area is going to be on Pleasant Hill Road. Okay? So if you're anywhere in here, and we have, you know, this would be on just the high tides. Your highest annual tide, there's about 5-6 months out of the year where you're within a couple inches of it. So my guess would be that these sections of roads would be wet, you know, for during the high tide. Then it would just drain off. I'm not an engineer, so I don't know what that means for the road. But let's focus in on Pine Point Road here. Just take another look at this. So a little hard to see, but this is existing highest annual tide. And if you notice, this is the clam bank. The parking lot of the clam bank is flooded, which it does. These ditches are no longer here. The town filled them. So that mitigated this problem, but the clam bank still does flood off the backside. So that's highest annual tide. You're just on the edge of flooding in there. Let's take a look at what might happen to the roads in here. 1 foot. And I left these little pockets of unconnected water here because I wanted people to see that, you know, this is tidal flooding, but if we have 6 inches or a foot of rain, these are areas where you have big pooling of water. And this is tidally connected right here. There's 2 feet, 3 feet, and 6 feet. With 6 feet, Pine Point becomes a barrier island again. Did everybody know that Pine Point was a barrier island? Okay, it was Maine's only barrier island at one point. Before they put in the rail line, and there was a little river inlet over here, which made Pine Point a barrier island. It's the only one in Maine. When they put the rail line in, they closed the inlet, and no longer is Pine Point a barrier island. But it would be with 6 feet of sea level rise. But they'd be also pretty wet throughout this area. So another thing we can do with this data is we can select a scenario and say, okay, well, how deep might the water be during some of these scenarios? So what this is a color-coded image of depths of 0 to 2 feet, 2 to 4 feet of flooding, 4 to 6 feet, and higher than that. And this is that highest annual tide plus 3.3 feet. So the highest tide of the year plus a meter of sea level rise. And you can see there's a lot of impact to this area. You can draw a transect, and then from there you can actually look at the actual inundation depths along the road. Okay. Actually, you know what? I think this is supposed to say, yeah, this is supposed to say highest annual tide plus 6 feet. Sorry. I was like, that doesn't look right, because this is showing up to 4.5 feet of flooding on top of the road. Okay. So that's highest annual tide plus 6 feet. So this is basically inundation depth on top of the road, transect A to A prime. To make a long story short, we do have a lot of roads that are at risk. I showed you that one image
the key is that they are not only our major access roads, they're also our emergency access roads. So Pleasant Hill would be the only one that would remain relatively dry the whole time. So 1 foot scenario would have a pretty significant impact on top of those. Okay. All right. Who's taking the Downeaster? All right. I didn't know what would come up this work when we actually originally did this. This was some interesting stuff to find out. All right. So to orient you, north is now this way. Crow's Neck, Pine Point, Route 9, Pan Am Railway, going into Old Orchard Beach, Scarborough River, Pine Point Road, Eastern Trail, da-da-da-da-da-da. We did similar work where we looked at how Pan Am Rail Line might be impacted by sea level rise. And this is just to put everything into a regional context. You know, we looked at this area right here, how that flooded. What we want to do now is look at the rail line, and we'll actually go in a little closer after a couple things. But this is just showing under the different scenarios that, you know, there's a lot of infrastructure that's at risk here. These are those color-coded areas. They are a little bit hard to discern, but this color right here is the highest annual tide plus 1 foot. There's a section right in here that gets hit by that. And then a little section right in here, I think, gets hit by that. But at 2 feet, there are very large sections of the rail line that would be impacted. So, and that's the take-home point. About 10% of the rail line in Scarborough would be impacted under a highest annual tide plus 2 foot scenario of sea level rise or storm surge. Okay. Another way to look at this is, again, those inundation depths, all color-coded. And to see something, you actually kind of need to focus in a little bit. So we'll focus in there. And this, again, is the rail line going all the way through here. This is the scenario of highest annual tide plus, again, I think it should be highest annual tide plus 6. Let me see if I messed that up. Yeah, it's plus 6, I think. Anyway, regardless of which one it is, there are going to be impacts. These are the inundation depths on top of the railway. So this is this channel right here. So that's not the railway, that's removed because there's a bridge. There's a bridge right here, that's removed. But there is between 3 and 4 feet of flooding on top of the rail line, basically. Okay, in this scenario. Take-home point again is that, you know, in a 2 foot scenario, we're going to start seeing some impacts. About 10% of the rail line in Scarborough would be impacted. All right. Summary, and then we can kind of go into some questions and discussion and stuff like that. Like I shared with you, and like you probably already know, about 75% of the marsh is high marsh, 25% roughly is low marsh. What we're seeing based on our simulations is that there is room for the low marsh to move into the high marsh. So we might see a change of species types. I'm not a biologist, so we have to talk to biologists about that. But what we are going to probably see is loss of high marsh because it doesn't have a place to go. It only has certain areas that are undeveloped where it can move into. So again, you've got a flat area where the low marsh can move into existing high marsh. You have some areas where high marsh is adjacent to fringing wetlands, freshwater wetlands. It can move into those. Or